What I want to do in this video is explore the idea of allele frequency. Allele frequency. And just as a reminder, an allele is a variant of a gene. You get a variant of a gene from your mother, and you get another variant of the gene from the father. And so when we're talking about the allele, we're talking about that specific variant that you got from your mother or your father. And we've seen this before, but now let's dig a little bit deeper. And to help us get our heads around this, we'll start with a fairly common model for this. And we're going to think about eye color. And obviously, this is a very large simplification. But let's just assume that we have a population where there's only two variants of an eye color gene. Let's first assume there is an eye color gene, and let's assume there's two variants. One variant, one allele for eye color, we'll use the shorthand capital B. Let's say that's the allele for brown eye color. And we're going to assume that this one is dominant. It's dominant over the other allele. Now the other allele we're going to assume is for blue eye color. And we'll represent that with a lowercase b. So that is blue eye color. And we're going to assume that this is recessive. So once again, this is review. Someone who has one of the big B alleles, the brown alleles. It doesn't matter what their other allele is going to be, because it's either going to be another brown or it's going to be a blue. They're going to show brown eyes. So this is going to be brown eyes. And this is going to be brown eyes because the capital B is dominant. The only way to get blue eyes is to be a homozygote for the recessive allele. And all of that, of course, is review. We've seen that before. But now let's think about allele frequency. And to think about that, I'll set up a very artificially small population. So let's say our population has exactly two people in it. Population has exactly two people in it, person 1 and person 2. And let's say we're able to look into their DNA and figure out their genotypes. So person 1, let's say, has a capital B allele, has a brown allele and a blue allele, while person 2 has two blue alleles. Now, given that we know the genotypes in this artificially small population, now we can start thinking about the allele frequencies, or the frequencies of the different alleles. So what do you think is going to be the frequency of the brown allele in this population? And I encourage you to pause this video and think about this on your own. So I'm assuming you've had a go at it. So you might be tempted to say, oh, well, it looks like 1 out of 2 people have it. Maybe it's 50%. But that wouldn't be the right way to think about allele frequencies. And allele frequencies, you want to dig a little bit deeper and look at the individual alleles. And when you look at that, you say, okay, there's 4 individual alleles in this population or there's 4 variants in this, or there's literally 4 chromosomes, I guess you could say, that they're carrying that gene in this population. And out of them, one of them is the capital B allele. And so we could say that that is going to be 0.25 or 25%. So once again, 25% of the genes for eye color have the capital B allele, have the brown allele. Now we can do the same. We can ask ourselves the same question for the lowercase b allele. What fraction of the genes in this population code for or represent the lowercase b, the blue allele? And once again, I encourage you to pause the video and think about it. Well, very similar idea. There's four genes in the population that are coding for eye color. Of them, 1, 2, 3 code for or are the lowercase blue allele. So that's 0.75 or 75%. 75% of the genes code for the lowercase the blue allele, while 25 are the brown allele. And I really want to hit this point home, how this is different than, say, the phenotype frequency. If I asked you in the population, if I asked you the percent of brown-eyed people, so now I'm talking about phenotype, what would that be? Well, there's 2 people in the population. One of them is exhibiting brown eyes, so that's going to be 1/2. And similarly, if I were to ask you, what is the percentage of people who are blue-eyed? That too would be 1/2. This person is one of the 2 people. They're exhibiting blue eyes. But allele frequency, we're digging deeper. We're looking at the genotypes, and we're saying, well, out of the four genes here, one of them is the big B allele, so that's 25% of the gene population codes for is the brown allele, and 75% is the blue allele. And this is really important to internalize, because once we internalize this, then as we'll see, the ideas in the Hardy-Weinberg principle start to make a lot of sense. And I'll do a little bit of foreshadowing. We can denote this, and this is just a convention that's often used, by the lowercase letter p. And we can use q, lowercase q, to denote the frequency. So p, lowercase p, is the frequency of the dominant allele. Lowercase q, the frequency of the recessive allele. But what's true here? What's true of p? What's going to be true of p plus q? What's p plus q going to be equal to? And I encourage you to pause the video again and think about that. What is this going to be equal to? Well, when we started off, we said that there's only 2 potential, that's one of the assumptions we assumed. We assumed there's only 2 alleles in this population, in kind of the allele population for this, in this gene population for this trait. So the frequency of the dominant ones plus the frequency of the recessive ones, well, everyone's going to have one of those 2. So there, if you add those 2 frequencies, it's going to have to add to 100%. And we see that there. 1/4 plus 3/4 is 1 or 100%. And 25% plus 75% is also 100%. So we could say P plus Q is equal to 100%. Or we could say that P plus Q is equal to 1, And so in the next video, we're going to start from the seemingly fairly simple idea to get to a richer and fairly neat idea that's expressed in the Hardy-Weinberg equation.